Okay, so welcome back. So to so let's quickly go through our teaching plan. So in week 8, okay, we have midterm. So midterm is going to be based on 1, 2, 3, 4, 5, 6. And okay, week 7 is going to be a lab session. But actually in the week 7 we also have some theories about the machine learning styles. So today we are going to finish. Okay, today we are going to finish the final lectures for the unmanned autonomous systems. From the system domain, like the general introduction for the path planning, what is control, and how the system looks like, and also going to conclude several minor components about SLAM. Okay, we remain in the last week. So as I just mentioned, okay, so this week, okay, week 6, next week, okay, we are going talking about the traditional machine learning, like decision trees, servo vector machines, and the regression process. And the lab session will be based on the lectures week 6 about the machine learning stuff. And later on, okay, in week 8, okay, we are going to have midterm. Probably by the end of this week, we are going to have our first assignment. Okay, first assignment. And later on, week 9, it's about the latest. I will not say the latest deep learning. We will start with the neural networks and the convolutional networks. And week 11, because this is a holiday. And also later on, I will collect feedback from you guys about the makeup lecture. Okay, because in this course we have 2 holidays. So because we have case studies, right? So we need to have a makeup. Okay, we have to make up for the probably on the weekends. So when you do the makeup, so usually it's on weekends. Do the makeup sometimes, right? And maybe in evening, something like from weekdays evening something. Because this is my first time. So later on I will share the Google Docs for you to Google Excel to collect your preference. Okay. And later I will summarize your preferences. Okay, so this is roughly our teaching plan. So it's quite close because so week 5, lab session midterm and 2 more lectures for the machine learning. Then we finish this course. It's quite fast, quite fast. Okay, at least to me. So any questions for the teaching plan? No. Okay, so let's go back to the. Okay, let's go back to quickly go through what we have learned last week. Okay, so this is the last week. So last week we are talk about the. Okay, from this, we talk about how to use the AI tools like DeepSeek and ChatGPT to generate the code, or you write the codes from scratch yourself and learn from the AI model generated codes. The first one is the read CSV file and the plot data. So let's say trajectories, right? So the trajectories, you try to read those data from timestamps, XYZ, orientations, and velocities to plot the trajectories. So this is a very beginning part. Later on, we plot the 2 trajectories in the same plot. Okay, so all the data and together with the example code is provided in GitHub. So later on, we provide the examples about ICP. So this is the basic or the principles of the LiDAR SLAM. So later on, we provide the examples of the ICP. So the objective is given to corresponding point sets. Okay. So for example, like this is 3D LiDARs, right? So on the top, this is a 3D LiDAR. Okay, so this LiDAR can collect or capture the 3D point cross as I just mentioned to you last week. Okay, a lot of color points, right? So the drone is flying at this point. Okay, the drone will collect the 3D point cross like the blue points. So for example, in this plot, there are 2 sets of point, the blue points and red points. So in the next time frame, okay, the drone move a little bit. For example, move a little bit. So there are some differences between those 2 frames of point cross, right? So the differences is because of the movement of the drones. For example, distance from the counters of this wall is going to be different. So the objective of ICP is to register or matching the 2 frames of point cross So the output is the translation and the rotation happens in this jump. So this is the principles of ICP. So later on, replicate the ICP. So later on, we are handwriting to explain a little bit about ICP. So the output is transformations. Okay, so this is the homogeneous transformation includes the 3x3 rotations and 3x1 vectors corresponding to the translations. So this is the difference upon cross the green points and red points. So by doing the registrations, we get the translations and rotations. Later on, we roughly introduce the position and orientation. So we mentioned how to transfer those paths from your angles to the continuous and generate the examples for those transformations. Okay, so last time we mentioned what is SLAM. So SLAM means to simultaneous localization and mapping, to do localization, to infer or to formulate the trajectories, simultaneously build the maps, right? So last week we introduced how to install the ROS. Okay, so let's say the examples we just mentioned. So after 7 iterations, okay, good, kind of converge, right? But this one, okay, from iteration 7, it start to diverge. Diverge means the solution getting worse and worse. So this is the challenge. So later on, we provide the tutorials for ICPs, right? ICP means like to matching the point cross. Yeah, last week I think you may not quite because later on I'm going to help you to like install the LiDAR SLAM package in your laptop. So it's very important to really understand what is ICP, right? So let me explain a little more about this part. So what it is. So first we need to know the objective of the ICP. So the ICP is iterative. This means to iteratively find the closest point. Iterative closest find the closest point. Okay. For example, there's a robots. Okay. At T1. Okay. Okay. The robot moves to the next point. Okay. T2. For example, there's a LiDAR on top. Okay. The LiDAR on top. So similar to so for different time steps, okay. So the LiDAR will scan the contours of the parameter. So for example, the contour is like this, okay. And after the robots, okay, the next point, okay, T2, okay, next time steps. Okay, the contour may be like this. Okay, so those contours is like consistent of the same point. Okay, a lot of points make up this contour. So why the contour shape is kind of very similar. So how to transform this contour from the timestamp 1 to the different timestamp? Okay, so how to transform? Okay, includes a rotation. Okay, together with a translation. So rotation is a 3x3 method to rotate. Okay, rotate. So the ICP problem is given two sets of the point cross. Okay, two sets of point cross. For example, the first set is X. Okay. The second, for example, this is from T1, okay? The first set of control is coming from T1. Okay, coming from T1. And for each PI is consist of XI, YI, VI. It's a point. Okay, for each of the inside this point set is for you. Will not actually be case, right? For example, like if you look at the first ones, of course it's very work. Okay, it's really and of course for the second time frame, okay, T2. So for example, this is Y consists of Q1, the Qn. Okay, so the number of points, with the number of points inside this point Z as T2, it's not necessary to be the same as T1. Yeah, it may be different because this depends on the environment, how the environment looks like. And for each QI, it should be X, I, Y, I, V, I, okay? So this is for the second frame of control. So the objective of ICP is even two sets of point cross X, Y. Okay, so for each of the constant, in this case, we have n points. We have n points, and each point is taken by X, Y, Z. So the objective of ICP is to here a point says X, Y to get the optimal R and T, okay? Get the optimal R and T. So probably if the R and T is perfect, okay? If R and T is perfect, R multiply Y plus T, okay? This means the transform, okay? The rotation of all the points, rotation of all the points, and then the translation, okay? This one should be probably equivalent to X. It means after you do the rotation and the translation, okay? This strip will be consistently aligned with this one. For example, if you do a translation, okay? Do a translation, it's going to be something like this. Okay, first you do a translation. You better translate the clip from right side to left side, okay? You do a translation. Sorry. This one is the translate first to this one, and for example, okay, T equals to T1 plus T2. Translate for 2 times. Okay, by doing the first translation, T1, okay, you get this one, and do a T2. It should be like perfectly matched with the original frames. Okay, so the T1, T3, so you have one vector. So for example, okay, R is a 3 by 3 vector. T, okay, this is translation, okay? This is a 3 by 1 vector. So based on this information, you can write down a homogeneous transform. So 4 by 4 matrix. It's like this. R 3 by 3. T 3 by 1. This is 0. This is 1. Okay. So this is the general representation. We have a part. So this is 3 by 1, 3 by 1, 2 by 3, 3 by 1, 3 by 1. It represents the translation and the rotation in one equations, in one matrix, So the objective of ICP is to solve this one, because as we know, practice. So what like the right now left difference of control from one to two. So this difference of control. So I would say this will not be exactly perfect. So in this case, can only do the minimization of finding the optimal solution. So this is approximately equivalent. So this in practice we cannot exactly find this to be perfectly consistent or perfectly equivalent. So we try to find the optimal problem. So this is operators. They are minimization. So to find the base R star T by minimize. Okay, by minimize. So this means the minimizations. This means minimizations. So to minimize this function, okay? Should be minus x. That means we try to do minus of the left side minus the right side. Okay? To minimize the difference between the left side and right side. Okay, the option of the minimization function is R. So we solve this problem, okay? To solve this problem, okay, exact solution. So for example, okay, let me quickly go through the solutions, okay? So as I mentioned, okay, what you want to get is this homogeneous transform, okay? Homogeneous transform. Okay, let's go back to the oops. Okay, so this is very clear for IC animation. So that's why it gives the equation 2. That's why it gives the equation 2. This is the meaning behind. So you get the equation 2. So actually this is the function. Okay, so this function. How do you think it's something like giving you solution in security storage? Security storage. So for example, if you have like, for example, this LiDAR are going to be like through LiDAR for the different cars. It's like roughly like around 1 billion points. 1 billion points. Quite a lot. Quite a lot. So if you process all those points at the same time, for a car, okay, all those things cannot be used at the same time. So in this case, this chapter is correspondence. So what is correspondence? So correspondence is objective of the correspondence is to reduce the computational load. For example. So for example, this is P1, okay? So you have a series point cross. Okay, so this is point cross from T1. And at T2, okay? Okay, this is T2. So if we look into the two shapes or two counters, so roughly in the T1, we have around like maybe like 30 points. Okay, 1, 2, 3, 4, 5. Okay, roughly, okay, 30 points. And for the second counters, okay, for second counters, roughly maybe they have like 31 or 32 points. Okay, so in real case, this may be 2 minutes, 2 minutes points. It's quite a lot. It makes it actually so the correspondence is can we only select the most representative points to reflect the shape. Reflect the shape. For example, okay, we only select very sparsely select the points. Okay, only select the red points, red circles point. So it's going to be something like this. Only have only 7 points. Okay, this you can kind of find the shape of rocket language. Okay, so those points, partly selected points are so-called the correspondence. This is correspondence. This can reduce the condition load. Also, for the second shape, we can do similar things. Okay, so in this case, okay, decrease from 30 to 7, maybe let's also to 7. Okay, so it came to the calculation you get. So the objective of the correspondence selection is to reduce the computation load. Okay, it's nothing new. So this is the so after that, gets this problem. So it gets n correspondence pairs, and after you do this information, you get the errors of the order receivers. So based on this, the next step is calculate the central of the extender. Central means to calculate the average value of all the points. This is like it. N means the number of points. Calculating average of T means one frame, I think it means the second frame. So after equation 5, okay, after equation 5, you need to calculate the, okay, like you get the central points. Okay, later on, you calculate the action matrix. So enter the part to 7 to 8. So why do you calculate this? Okay, looking at the graph and you get. So after you calculate the edge, you get the so so SVD means is so okay. We have learned the metrics. Just let you understand what is metric. So now we have a whole metric. Okay, so let me ask it in other ways. So if I have a whole metric, so what's the meaning of that? And let's get to one of the application of the metric. For example, I can use the so what I want to ask is about so SVD is a very good way to explain what is a matrix. Okay. If we talk about locations, okay. If we talk about locations, it's going to be location matrix equals 3 by 0. So why the size is 3? You don't have so if you look into a 3 by 3 matrix, okay, for any of the matrix, for example, like H, so for any of the H, so for any of the 3 by 3 matrix, okay, for each of the 3 by 3 matrix, the H can for the SVD, okay, for SVD, this can be decompensated with first law, okay, okay. First of all, you can find the orthogonal basis. First, you will know what orthogonal basis is. For example, for the 3D coordinate, get 3D coordinate. The orthogonal basis is okay. This can be easier to understand. So for x, y, z, okay. For any of x, y, z, we can have an orthogonal basis of x, y, z three directions. The orthogonal basis is composed of the direction vector of the three axes. Direction vector of the three axes. This is the orthogonal basis. So the three vectors. So the three vectors. Okay. The three vectors. Okay, make up the orthogonal basis of the 3D coordinate system. So the key features of the orthogonal basis is the three vectors. Orthogonal means the multiplication of any of the two vectors is 0, is 0, x, all of them are 0. Okay, this means the three directions is 100%. Now related to okay. So this means this is orthogonal basis. Actually, for any of the points, okay, x, y, z, for example, any of the points x, y, z. For any of the points within this coordinate system, okay, it can be represented by a orthogonal basis. Is that correct? So for any of the point P should be able to be represented by x multiply ex plus y. It means any of the points can be represented by the coefficients of the orthogonal basis. And coefficients of orthogonal basis of y and z. So let's begin the relation. They define the orthogonal basis of the matrix. Orthogonal basis for the matrix. So this is orthogonal matrix of the matrix. Okay, so this can be represented by. Okay, so what's the meaning of this one? It means for any of the H matrix, we can find the orthogonal basis of the matrix. Okay, written by this limit. Okay, so the left side U and V is the eigenvalues. Okay, so if you still can remember, the H should be represented by lambda 1, lambda 2, lambda 3. And this is orthogonal basis. So what's the meaning of this? This means that the condition for the find the orthogonal basis. First, we will investigate the coordinate system. We find the orthogonal basis first. And secondly, try to find the coefficient corresponding to each orthogonal basis. Okay, so it means for lambda 1 and lambda 2, lambda 3, the eigenvalues. Perfect. Okay, so eigenvalue is coefficients of each orthogonal basis. So the H matrix will calculate the single value decomposition for this one. Okay, this is to find the orthogonal basis of the H. So later on, if you read this areas, okay, and make the paper references. Actually, then you know the physical meaning of the eigenvalues. Physical meaning of the eigenvalues. So actually, the physical meaning of the eigenvalues is of the one. Physical meaning is all the sequence of control. Okay, has to be Marking the code between the components. Okay? Giving different difference if you want to know what to do. But anyway, so this is corresponding to the orthogonal basis of H. And unity is going to be of the any values of the matrix values. So in MATLAB or in Python, you can take the values depending so later on, okay, so after you get after you do the SVD decomposition, you only get the location is one thing, and after you get an R, you can get a T. So something like this. So why? Because okay, this is one variable R. If you get the R, so this is the arguments behind. Okay? Then we also provide some here's about the components. So okay, to achieve the last method. So finally, if you get those translations, okay. If you get R and T, it means for the two time frames. If you get R and T for two time frames, okay. For example, this is we can write down the matrix. Transformation from epoch from constant 1 to 2 is equivalent to RT01, okay? You get this transformation. And later on, you accumulate all those transformations. Okay, you get it. So how to accumulate? Okay. For example, the robot is moving from constant 1 to n. This one should be equivalent to from first to 2. Multiply from 2 to 3, multiply from 3 to 4, multiply from n minus 1 to n. So this by doing the multiplications, you accumulate the motions and get it together. Okay, so basically the principles behind the ICT tutorials learn is like this. You get the motions and you accumulate the motions, you get the trajectories. Okay, practice. So as we mentioned last time, okay, the Python has limitations like the speed and the community issues. So if you're talking about learn, so the community for the Python is quite small. So that's why we go to ROS. We see double class. So last week we installed the ROS. Okay, we installed the ROS. So anyone still did not finish the installation of ROS? Okay. Perfect. Okay, you all finished the installation of ROS, right? So after you install ROS, we provides the package. Okay, so after you install ROS, what you want to replicate is the GeoSend. So GeoSend, the I4 is right now the notion along. So this is the package that combines the measurement from LiDAR. Okay, so this is the LiDAR. Combine the measurement from the LiDAR and also combine the measurement from an IMU inside this LiDAR. So let me show you how the data looks like. So if you have like the one take break, or take break for 1 minute. So I see already know it's a package, it's called Postnet, okay? So please download the data set during your break. Okay, download it. Go to this package, Postnet from my GitHub page, and there's a data link, the Slack data set. Create the screen, download the data set to your laptop. Okay, 10 minutes break, 10 minutes break. Download the data set. Data point quality is part and after the process of SVD, what kind of data you get like the small number of cloud or just nature. Oh, so the SVD is, I mean, this is the optically selected point cross. For example, down this is millions point cross and parallel. Okay. So first we select the correspondence. So it's the correspondence right with the strength. For example, like smart state select like 100 points. So this is what the correspondence selection. So after that, we play with the 100 points based on the SVD. So SVD is another later. Okay, I got it. What is the process of select the way and the data from I raised before, just like mostly random selection. For random selection. Okay. For example, you have 1 million points, right? You can just use like random selection from okay. We can set the how many points we get we need. Yes, usually we do something like this. So for example, we have a lot of home process. First of all, we will most grid, grid. Oh, okay. Yeah, and then you select 1 point and grid. Oh, that's it. Okay. That's really is very interesting and use that for analyzing the radar data. Ah, yes. And that can be also used for see the image. Yes. So like CPA. So CPA like the principal component selection, they are all talking about the SCPD. So SCPD means you get on total basis. So if the eigenvalues of any rows of on total basis is large, means this is included. Okay. And another question. How can we set the number of the
the point. For example, there is 1 million point, and actually, how can I know I can set 100 or 200 and 1,000? Usually, it's experimentally determined. Experimentally determined. Previously determined based on expenses. Expenses. Because that's the wrong part, right? You must parameter based on volume. So the number could be dynamic. Usually, offset is dynamic. It is the stable number. Yes, fixed number. Okay. Fixed number. Usually, you will not set the number of points, set the size of the ring. For example, how many points you can expect from the factors. In this case, you will each of three, you know, some points. Okay. It's very important. Engineering. Yes. It's very important because, for example, in some sparse environment, if you don't have enough points, it's going to be trouble. Okay. Saving time is saving money. Yes, exactly. Especially for real-time applications, to ensure it's accuracy is guaranteed and efficiency is guaranteed. Okay. Okay. Oh,
Okay, so let's move on for the rest. So the Liu Shen. So in the slide, you can see, okay, we are like talking about the, so in the slide, we introduced the Liu Shen, so LILSAM. So this package is developed by this is also one of my friends. So currently he's in a company already. So previously he received his bachelor from Qingdao University and MSc from Shanghai University. Later on, he has several years in US. It's different Institute of Technology. It's not that famous, but it's lays a very good team in that institute. So he received a PhD there. After that, he had like 2 years of postdoc research in the MIT. So in the Professor Ross research group. So at that time, I would say you are quite lucky because previously, like several years before, we don't have such strong package to get learned. Okay, so at this moment in 2018, so there's no package free available online for the LiDAR student. So during his PhD in Stephen Institute of Technology, he developed this package and open source. So this package you can see from the GitHub, there's a lot of stars. 3.7K. Okay. Develop a package is very strong. It's blah 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 something. Okay. So show me the star. Okay. Star means someone is using your package. Okay. For example, in the future, if you found someday like you go to the job market and in your resume you say okay like okay you say I have a package I maintained and like He Kaimin, do you know He Kaimin? Am I is He Kaimin is like okay, let me tell you one more story about He Kaimin. Okay, so for researchers, we look into the citations, right? So Kai Min He is a top one student from Guangdong province in 2020 something. So very interesting thing is if you look into the several very famous researchers in mainland China or this world, they're all from Guangdong province. Okay, like DeepSeek. Okay, Liang Defeng is coming from Zhanjiang city, Guangdong province, right? So Kai He is also from Guangzhou City, okay, Guangdong Province. So yeah, I want to say is like if you are talking about 666, wow, it's a good number today. Oh, okay, it's quite symmetry. Okay, 668866. It's a good day. Yeah, it's a good day. Yeah. So Kai He previously is in Facebook. Okay, now it's Meta, right? So he developed a ResNet. So ResNet is almost a very inspiring work on the machine learning, deep learning stuff. So you see, so if you look into the machine learning, okay, the keywords very interesting. Okay, so two keywords. So previously he is working on the computer vision. So later on we have AIs. He's working on machine learning. So if you look into the machine learning, okay, select keywords. So the top citation is Chris. Wow, from UC Berkeley. Okay, so the first one is looks like maybe from China before. So top one, okay, Nobel Prize, okay, Hinton, Kai He, okay, you see, you know the position of this. So if you go to academia, okay, so of course Kai He last year he go to MIT, go back to academia, okay, from Meta. So this is your profile. For example, in your resume, you say you get like more than 100 more than like 10K of citations is going to be great. Okay. 0.6 0.6 million of the citations. This is crazy. So similarly, if you look into the Nielsen, okay, around like 3.7 thousands of the stars means many people are using this package. Many people are using this package. So let's say the package, if you look into the graph, you can see roughly see the results. It's like the get trajectories. Okay, let's simultaneous localization and mapping. Localization means you get trajectories, right? Mapping means you build a map of the environments. So this is okay. This is okay, Dr. Shan. Okay, take a handhold system to this is LiDAR. This is camera and computer inside with the IMU inside. Okay. At the time, this is very famous robots. Put the system on the top. We collect data. We collect data. So we can do SBM validations. So roughly, okay, the information in this is okay. The input includes the IMU, okay, accelerations and the linear angular velocity information. The 3D point cross is the points. So GPS is optional. So today we are play with the IMU and the GPS, IMU and the LiDAR. So IMU is also it's like a supplementary to the LiDAR. So LiDAR is good enough and IMU can help you to copy some high dynamic motions. Okay. As we mentioned in the slide, so first we need to install ROS and from the step 4, okay, from step 4 is to download and build the system. So I assume you have already, I just assume you already have downloaded the ROS and install the ROS. So it's clear. You can see the screen, right? So okay, let me clean everything. Okay. Okay, nothing inside. I have a photo. Much better? No, much better. Okay. So first of all, okay, we need to download the data. Oh, okay, several commands. CD. CD means to get into some specific folders. Okay, get into some specific folders. So for example, you need to get into the SRC folder. So okay, so this command is to generate the folder. And generate the folder. General command is so not complicated at all. So just very simple command is free now. So mkdir.c and then go back to the so git clone. Git clone is a GitHub command to download the data, download the package. So how to understand this command? Git is GitHub. Git clone is to copy our data based on the thing. Okay, try to understand. So for example, in the future, if you want to download any of the package, okay, the link can be found from code HTTPS. Okay, copy. Okay, so this is the full code. Full link of the code. Okay, so it will download the code. One more run. Okay, into the action and enter. You can see the previous one. I'm going to go for finding. Okay.
You can just go back. So this is fine. So I think you want to be far, right? So I'll say that will be the high. So let's okay. You can go back to the previous months. So let's copy the name. Also, we can do the same thing now. So go back to the slide. Okay, go back to the previous photo. Okay, go back to the previous photo. And input the taking rate. So this is the command compiler code. This is command compiler code, okay? So replicate first, okay, later on you can try and I will be here to solve the problems. So this is the compiler code. For example, it's the input on package. Here, so IBM. So IBM is a model for Google, by Google. It's mainly used for operation of the language. So often the data is like. So this is because of the problems of the because we install the 2004. No. So the package is different. The package is provided with any country. Mention the slide. So what I do is, so this is package, right? Inputs code starts, okay? So let's say we open the code. Let's say we open the code, okay? I will define the code. And as mentioned in the slide, you see the error is coming from your utilities. Okay, from Nielsen includes photo, Nielsen includes utility, and find the line. So also copy the code. Okay, copy the error to the AI, to the compiler, the operating system. So the solution is provided in the slide. So what I need to do is change. Okay, change this line. Open cv.edge. Okay, this one. Okay, change this to. Okay, you can just comment this line. Okay, slash is comment. Okay, and after you change this line, okay, change this line. This line is in the ASM photo, into photo, into page. Change this line. Okay. And you will compile again. Okay, a lot of errors, right? A lot of errors. So the error is coming from the to be coming from the same place. So actually, I already have a package that is full of errors. So if I want to like maybe to go through the process. So for example, if you develop a package, only one package from the lab, okay, you will have a similar problem. So all the problems like what we need to learn. So the errors is coming from the should be coming from this in the same place. Because previously the code is compiled based on a couple of blocks. So because this is like one thing, the other when you change this line, the element to 40. So the green, okay, that I'm going to have to for you on some of the texture. Conflict comes out, we have this for you. Okay, so still some errors inside. So if I, because I already have the, all error fixed motion of the code, so I still just to go through those errors for you, okay? So if you look into errors, this is coming from this is coming in a PCL. Yeah. Okay, so if you look into the reminder, okay, indications. So the error is coming from the map optimization, So one solution, okay, let me put it to this one. So for example, this is the AI models, AI first. I can just search this into this compilers or this AI first. And later on, I will let you know where the error is coming from. Okay? Okay, so yes, the solution is flat. The solution is flat. So we need to define the flat and over think on the plan. Define the plan first, and later on you can include this head files, include the head files here. So let me show you the correct version. So this is the correct version. This is the correct version of this thing. I have fixed all the issues. I have fixed all the issues with the one, two, three version. This I will show you. So let me look into I'll show you the codes, how we change. Okay, I have delete all of compilation results. So this is the correct version. This I will show you. Errors in a compilation because all the code is then the platform will change. For example, later on we are in 1.35 info. So if you upgrade the version of the function, you get different errors. So in this software today, I can only teach you errors are encountered in the software. What the process is looking the same. So if you get errors, no worries. You can get errors and not the errors from the listening to copy to Google, you can be faster. So now we can look into the arrow errors potential to solve errors. Or maybe you can take time. Okay, take time to solve errors. Okay, 10 minutes. Let's try it. You can solve the error. But finally, I will provide you a correct solution. Okay, take time, 10 minutes. Okay, finally, I will provide you with the correct solution. So in a compile process, you get errors, right? You get some errors. Okay, I'm sorry. So you can just replace. So you can just replace the head files from here, okay? Replace all the head files with this new head file setup. So you can find this in the pulse length features. Okay, you can go to the pulse length features. Okay, you will find the solutions. Okay, take the time.
attention. So let me show one more time, okay? Let me show you one more time. So some of our students have successfully succeeded in comparing. So first of all, you need to change, so this is the package, right? You need to change your CMake list, change this line, okay? Column list 11. So previously list 11, you need to change this to 14. You need to change this to 14. So this is the first part. The second one is the head files. Okay, just replace from line 56 to the up to the top with the head files here. Okay, so head files is in the course length. This package issues the first issue solution for this thing. Okay, copy this and replace the head file. So as I can see, several of you have already finished the compilation of the Liusen, okay? So after you have finished the compilation of Liusen, so the next step is to, you can download the data set. So in here, okay, there's, so I mean, this package already provides some data set. For example, this is sample data set. You can download the park data set or the garden data set, okay? So let me replicate the demo so you can download the, okay, the park data set. Okay, you can download this one. It's like around three gigabytes. You can have the direct access to the Ubuntu system in this one. Okay, in this, you can directly have access to the photos of the Ubuntu from the file system of the Windows. Okay, the home. Okay, you can download the data set to somewhere in the Ubuntu system. So is download data set. So for the page 85, okay, 85, 86. So for this connection, okay, if you, okay, this is not necessary. So this is not optional. So it only helps you to better use the base code for the comparing. So you can also can skip this during the class, okay? 84, 85. After lecture, you can try yourself after class. So for the three page, okay, connect to the step four. Okay, step four, connect to the IDE. Okay, you can skip this one. Okay, you can directly go if you compile successfully. You can directly go to the step five. Okay, go to step five to run the code. Okay, go to step five. And for the example data set, okay, example data set, you can download the pub data set. Okay, so you need to check the root topics. You need to check the root topics. So for example, okay, we change the topics here. It means less more options. Okay, I have successfully downloaded the pub data set. So I will copy the data set from Windows. Okay, download to this folder. Okay, so I can look into the go to download folder. So if you look into the data set, the pub data set,
If your something like this. So this is the part data. Of course, this is in the part. You should see something like this.
Okay, so your attention, please. So let's summarize the main steps to replicate the demos, okay? So first of all, you need to clone. Clone means download the data, okay? Download the data from the website. So after download data, you can use the VS Code. So how you can have access to the codes through this VS Code IDE. So as I mentioned, because of the version problem, so because the LeoSim package is developed based on the 1 to 18. So for this 20, okay, because we are installed 120, so we need to change a little bit about the head files. So the head file is located in the, okay, so this is the package SRSA. So listen include, okay, there's the utility files. So in here, okay, the head files is from this, okay, include means include some head files. Okay, you can replace this with the head files are provided in the Tosland. Okay, in the Tosland. Okay, issues. Okay, replace with this tor file. This us. So for example, that's us. And after that, you compile the code again. Okay, so compile the code again. It will find it will succeed. Okay, it will succeed. So after the code is succeed, okay, you need to download the data set. Okay, download the data set from the package. For example, like in the slide, we also provide the dataset link. Okay, this is example dataset, right? So if you open the link, it will direct you to here. So you can download the PAC dataset. Okay, download the PAC dataset. This is a very typical dataset. So after you download the dataset will download in the Windows systems, right? In the download folder. So go to this, because in my laptop I have versions of it. So go to a 20 version, okay? And the home, okay, this one's my name. And go to, okay, you can generate a new folder or just copy to this folder. It's also okay. It's very similar to Windows. So after that, okay, okay, the compile is doing, yeah. So after that, for example, my data names. So, okay, this command is to open the data sets. So the compilation is almost succeed. So if you open the data set, finish completion of the comparing. So almost 95, like 100% means you finish the compilations already. Yeah. You can see the assumption of my laptop. You see, okay, this is the usage of the CPU. Okay, because it's doing the comparing. So this one. The H top, you can see the usage. For example, in my CPU have like 22 cores, 22 cores. Okay, it looks it's a big number. Actually, it's weak. Yeah, actually it's weak. So let's choose, right? Very slow. So you see the usage of the CPUs. Okay, it's mainly use the third GPU, third cores. Okay, it's quite slow. So to see the usage of the CPU, you can just input HTOP. Okay, HTOP, you're going to see the results. HTOP, you're going to see the usage. if you cannot, if you get some errors, maybe you didn't install a HTOP. The command is like sudo apt get. This is a general command to install any tool. This command to install a desktop. Okay, I already have. That's why I can see this. Okay, so this, okay, the code is successfully compiled, and you can go back to the slide. So the command to run a command to run result run a real things like this. Okay? Run the code, you get arrays, right? Play the data, okay, you get some results. Okay, so get results, right? So this is what you're expecting to achieve. Okay. So finally, okay, let me quickly go through about the structure of the code. Okay. So this is the general package because in this course we didn't introduce the C double plus, right? We didn't introduce the C double plus. So generally the C double plus is slightly different with the Python. So the C double plus is very efficient, especially when you implement some very complex algorithms. It's very efficient. Okay, very efficient, very efficient. And the structure of the code is like this. So the main code is in the SRC photo. SRC photo includes the like the feature extraction is corresponding to the correspondence detection. So for example, ICP, we have the correspondence detections, right? So this is the feature extraction code. Okay, so yep, it's take time to learn. Yeah, if you want to dig into, take time to learn, and also the IMU. So the IMU parts is based on the some existing libraries, and this is the optimization parts, how to combine the measurements from the lidar and from the IMU. So this is the code. If you want to, maybe so in the final year project, okay. So if you are, you can select some projects from the supervisors, right? If your project is ready to learn, okay. So you can take time to dig into the package and to know what is behind. So let's go back to the topic of artificial intelligence. So any of this slam, any of part of the slam can be improved with AI. So for example, we mentioned like original point cross from 3D LiDAR is like 1 million points, right? So how to select the most representative points? Okay, so AI can work, right? And also if you have different information sources like 3D LiDAR and IMU, so how to tune the different weightings when you do the sensor fusions, right? So this can be benefited by the artificial intelligence. So a lot of parts. And also for the detections, okay? So for example, we can get the point cross. So how to detect the trees? How to detect the objects in the front, maybe the cars, the bicycles, the people, pedestrians, how to detect those objects from the 3D point cross. So AI can work, right? So this course can cover a lot of things, but limitation of the times. For example, those pillows are trees, right? So for example, for the drones flying through the forests, you need to detect what's in the front. So the AIs can be used to detect those pillows, those trees, okay, based on those AI algorithms with 3D line upon cross. So AI can be used for many of almost throughout this package. Okay, so it's going to be a paper. Okay, I'm not joking. Okay, and this can be a paper. So this is roughly how the package looks like. Okay, how the package looks like. So how many of you have already finished the replicated demos? Hands up. One, two, three. Okay, you can try later on. Okay, in a art class, you can replicate demo in your laptop. And any questions, okay, feel free to raise the issues from the GitHub. Okay, if you have GitHub issues, you can raise the questions over there. Okay. So yes, in my slide, always I think I prepare too much. So this is another example. Actually, I wish to like go through the example with you. So this example is like how to generate, for example, just now, okay, the Leo thing is existing package, right? This is open source existing package. So this is another part. I mean, another part like I wish to introduce how to generate a ROS package, generate a Slam package from scratch, from zero, okay, with the help of AI. So um, I think I may not have time to go through everything. So let's quickly go through the main ideas. So this is a problem of like how to generate or develop a loss slam package from scratch. From scratch. So first, okay, the requirements is like you need to have a laptop with Windows operation system at least 11, okay, 11. And also you need to have 30 G space at least in your laptop. So basic understanding in C++ and ChatGPT tools such as the DeepSeek or GPT-4o. So the task is giving a low spec file. Low spec is a format to save the data, right? For example, the park data sets is saved in a raw spec raw spec format. So read and save the 3D point cross from to the PCD files, which means the so raw spec is a sequential data set, okay, saved in a raw spec, right? So the first part is like we extract the point cross from the raw spec to a file, okay, to a single file. So for example, like image, okay, sequential image, we get the videos, right? You can extract the videos into a separate image. For the raw spec data set from the LiDAR, it's like sequential LiDAR point cross. You can split them into the different frames of the point cross. It's like image. So the second part is like follows procedures from DeepSeek to set up the project. Last one to run the code and save the PSD files. And later on, we have another task is to perform okay. So this is some major steps to generate a ROS package and set up the XML file. So this is the configuration files of the package. So the whole package, you can download the whole package from the TOS link. So this is finally what you're going to achieve, okay? Finally what you're going to achieve. So for example, in this package, there are several files. Okay, there are several files. CPP means the formats of the C++, okay? If we start with the CPP means it's .py means the Python code, right? .cpp means the C++. So for example, like NDT is another variance of ICP. It's much, so ICP is only like in a classroom to let you know what is the Punker registration, but in practice, ICP is not useful. So we need to use NDT something like to achieve accuracy. So we provide for different CPP files, rows nodes, and the four CPP files associated with for different examples with certain functionalities. So for example, the first file one is subscribe the 3D point cross from the raw spec and save the point cross to the PCD files. It's like save like image. Okay, extract the, for example, okay, extract the image from the video flow to the image. So this is to subscribe the point cross from the raw spec to the 3D point cross data, okay, frame by frame. So the second one is read the data, read the PSD file to perform the ICP to get the transformation. The transformation should be 4x4 matrix, homogeneous matrix. So 5.3, 5.4, okay, so you can read those packages. So if I have time later on, I will like go through with you to generate those package from scratch again, okay? So these are some, I mean, subtask or the after class task, okay? So for example, like how to replicate some more complicated demos. So this is a tutorial, another tutorials about NDT. So as I mentioned, like NDT is a variant of the ICP. So you can refer to this tutorial to see the to see the theories behind. So I still want to emphasize, so yeah, SLAM is simultaneous localization mapping is a big problem. So I would say in the past 2 weeks, I tried to, so as you can remember, the first minutes of the last week, I let you know what is SLAM results looks like. Right? You see the mapping process, right? Then I dig into those environment setting up, the installation of ROS and Ubuntu, and finally you replicate the demos, right? So those are only like one like 10% of the SLAM. So you can replicate demos. So if you want to really learn, you need to look into the code and run the code and see the results, analyze the results. So you can see the pros and cons of the SLAM algorithms like Liu-Sen. So for example, you find some limitations, you can look into problems to solve it. So always a learning process. I mean, the results is not that important. The process is more important than the process. Yeah, procedures. Yeah, process is more important. For example, just now I think I'm not sure if you have get aware. So just now we see some errors, right? So how to solve the errors is the most important. Okay, you can replicate demos with the slides. You're good. But if you can look into the errors and not get fair with errors and solve it, you're great. Okay, solve errors. Because in the future, like if you get into job markets, you need to solve the new problems. Okay, instead of solve the same problems, you need to solve the new problems independently. Independently. So let's make a quick review because as you know, but at the beginning today we are going to talking about the autonomous systems, right? The systems, the planning control stuffs. But yeah, maybe I will put this in the later lectures. But let's make a quick review for the last week and this week. So we mentioned the Pythons, right? Mentioned about Pythons or the basics grammar for Pythons. And later on, we introduced the slang. We introduced the slang and how to replicate the Liu-Sen. So there are some resources for the learners like Pythons. Okay, you can look into the communities, and this is like one for the class from Russia. So you can look into this one as well. So the next week we are going to talking about. Okay, so next week we are going to talking about machine learning. Okay, we start from the regressions and starting to play with equations. Okay, start to play with equations because for the regressions, like from linear regressions, logistic regressions, and later on we have decision trees. We are going to have equations. We are going to introduce the gradient descent. Okay, and how to. Okay, also later on we have neural networks, right? How to optimize the neural networks. We are going to have equations. Okay, so any questions? So if you get questions in replicated demos for Liu-Sen, okay, feel free to raise issues in the GitHub package, okay, in the GitHub repository. So if there's no questions, okay, so yes, that's all for today's lecture, yeah.